Hello everybody, this is the first video of chapter 8 of the statistical learning course. The purpose of this set of slides or chapter is to present the principal component analysis method. So this covers parts of chapter 10 from the ISL textbook and chapter 14 of the ESL textbook. Principal component analysis, or PCA. PCA is the short expression for principal component analysis. This is an unsupervised learning technique aiming at reducing the dimensionality of a data set. So often, in many problems, we have a very large data set, and large in the sense that P is large. Not necessarily N. N could be large also, but P is large, so we have many, many, many predictors. And in that case, it's very hard often to build models based on many, many predictors. So it could be convenient, at least from an interpretation standpoint or from a stability standpoint, to obtain a data set which has a lower dimension but which summarizes well the information contained in the initial very large set of predictors. Okay, so we'd like to summarize the information provided by a very large set of predictors into a smaller set of new predictors that we can construct from the original ones. So these new predictors we could construct for the original ones, and which would be less numerous, can be used in multiple ways. So the first approach is that these new features or new predictors constructed could be used in a supervised learning regression model, which would be called as a principal component regression. So sometimes we want to have we have a very large number of predictors. We construct new ones, which hopefully summarize as much as possible the information in the original set, but where we have much less new predictors. And if we apply a regression on these new predictors, the idea here is because we have much less predictors in the new set, the variance of predictions should be much smaller. So it's very useful to come up with these new predictors. Alternatively, these principal component analysis methods, they can be involved in the construction of a factor-based time series model. I don't necessarily want to delve into too much depth about explaining how they work, but the idea here is that often we have a very small number of quantities which impact a very large number of observations. Okay, so for example, if you look at stock returns, typically when there's a market crash, all stocks tends to plunge at the same time. So the idea here is that like there's one quantity which determines if we're in a good economic health or bad economic health, which would impact simultaneously a very large number of other variables. And it would be much more convenient to model the like a single variable at a time instead of modeling the behavior of, let's say, there are 1,000 stocks available, than the behavior of these 1,000 stocks simultaneously. Okay, so for that reason, it's more convenient to model the dynamics of fewer variables than a large number of variables. So factor models often use the idea of constructing a lower number of variables which summarize the information provided by the initial variables, and then modeling these lower number of variables instead because it's more convenient. Okay, so we can see that PCA can have many usefulness in many types of applications. These are only examples, but they should motivate that using PCA is relevant because we often want to reduce the dimensionality of a data set to summarize information provided by a large number of variables into less a lesser amount of variables. As we mentioned, principal component analysis is an unsupervised learning technique. So there's no response variable considered within the data set. We only have explanatory variables, and we want to find a relevant pattern within these explanatory variables. Okay, so observation I or data point I simply consists of p predictors. So xi1 until xip are the p predictors for your observation I. In this chapter, we will derive the entire theory later on, but we will first start with a motivational example, which is more simple and should make clear what we're trying to accomplish with our principal component analysis method. To do that, let's consider a fictitious data set that I've simulated in R using R. The data set contains exactly n is equal to 50 observations, and each observation has exactly two predictors, so or covariance. So there's predictor 1 and predictor 2. How were these simulated? Well, we had the following algorithm to simulate these. Okay, so for we have u1 until un, which were IID uniform minus 1, 1, and epsilons 1 to n, which were IID normal with mean 0 and variance 0.02. Okay, so from that, clearly we see that the magnitude of the u's is greater than the magnitude of the epsilons. And furthermore, the u's and epsilons were simulated independently. So in that case, what we did to generate the predictors for each observation, we did the following. The first predictor was simply set as ui, the uniform random variable, and the second predictor was set as 3 times ui plus epsilon. Okay, so basically the second predictor is almost 3 times the first one plus a bit of noise to slightly shift its value. Finally, what we did to get the final predictors is the following. We've centered the predictors. Okay, so principal component analysis is always apply on zero mean predictors. Okay, the way the methodology is constructed, we have to consider predictors with zero mean. So to do that, well, there was simply a demeaning procedure where the observations were centered. So the first predictor for each observation was taken as the original. So here pre stands it's before the final predictor. Okay, so we took x1 pre and we removed the sample average of the first predictor in the original data. So the final data was centered and its sample average is 0, and we did the same for the second predictor. Okay, so we see here using these equations, we've simulated two predictors to our data set. So what does the data look like? It looks like the following. So here this is the first predictor that was simulated in the data set. Here this is the second predictor, so we can see that all dots correspond to simulated observations within the data set. And what happens here? Well, this is in fact a two-dimensional data set. We have two predictors. But the idea here is that probably if we want to summarize the information contained in these observations, we might not need a two-dimensional setting. Maybe a one-dimensional setting will work well. So instead, what we could try to do is to, if we plot a straight line here, sorry, it should be straight. Instead, if we consider the straight line and try to determine where on that line the points roughly fall, it might summarize very well the information about all these points. Okay, so basically we could try to find the projection of all points on this line. Maybe this one would be here and this one would be here, and we can see that the observations where their projection on the line is very close are pretty similar. Okay, so here these observations would be very similar to each other, etc. So we could see, or we could think that there might be a way to do a very good job to summarize the information provided by these data points with a single quantity for each observation, which would be where on that line would you fall, and the departure from the projection and the data point looks somewhat minor. Okay, so we should be able to do a reasonably good job of summarizing the information provided by data points with a where we summarize this information with a single quantity for each observation instead of two. And this might be convenient because dealing with a single predictor is more convenient than dealing with two in modeling. Okay, so before doing some more illustration of what we're doing, we have to recall some definitions of linear algebra. So I'll read the definition. An orthonormal basis, so this is what we're defining. An orthonormal basis of the set, the space Rp, is a set of p vectors b1 until bp in Rp, where here bj, the vector bj, is the column vector represented by bj1 until bjp. So we see that bj is a vector in Rp. And this set of vectors is said to be an orthonormal basis if we have the following. So if whenever j is different than k, the vectors bj and bk are orthogonal. So orthogonal means that their scalar product, defined by this, is equal to 0. And if each vector is normalized, so the norm of each vector, which is the square root of the scalar product between b and itself, is equal to 1. So this is the normalization condition. So we say that a set of vectors forms like an orthonormal basis of Rp if there are p vectors that are orthogonal and normalized. So orthonormal stands for orthogonal and normal. And we say that these form a basis of Rp because for any vector y in Rp, such vector y can be expressed as a linear combination of the orthogonal or orthonormal vectors. So each vector y can be expressed as the sum across all vectors of a coefficient Cj times the vector Bj, where of course Cj differs when we with respect to y. Okay, so if we take another y, then the Cj's would change, but the Bj's would remain the same. So the most well-known basis is the orthonormal basis is the set of unit vectors. Okay, so for this example we're going to show, we'll go back to the previous example in 2 dimensions where we had kind of this diagonal data set. So we'll consider 2 dimensions only to make the explanation more clear, and later on in future parts of the chapter we'll generalize this to higher dimensions. So the most well-known orthonormal basis is the set of unit vectors, where the first vector could be 1, 0, and the second vector of the basis could be 0. So it's possible to express any data point xi in the data set as its first coordinate times the first unit vector plus the second coordinate times the unit vector. Okay, so these elements here represents the weights for each vector are basically the elements of the vector, which represent the coordinates of the data point when we use the set of axes 1, 0 and 0, 1 are these basis vectors. So for these, let's define s square xj being the sample variance of the jth coordinate in the entire data. Okay, so here what we have is we can calculate the sample variance by this formula, and recall that each predictor were centered, so their sample average was 0, so this guy disappears. It is simply the sum of squared jth predictor or the average of the squared predictor across all observations of the data set. So in our example, if we take the sample average of the predictors, for predictor 1 it's 0.28, 0.289, and for the second predictor it's 2.773. So this basis, orthonormal basis, is known as the canonical basis. But what we're gonna state next or explain next is maybe the canonical basis is not the best way to represent our data in that case. Maybe another set of axes might be better suited to have a better depiction of our data. So if we consider the following basis, so here I want to explain how, well, I can't explain how these were obtained, but if we could have considered the more natural orthonormal basis uh, uh, in this context, where here a1 could be this vector and a2 could be this vector. So uh, how to come up with this? It's basically to find the a1 was simply the normal vector, so the vector of norm 1 for which the magnitude of the third element was 3 times the magnitude of the first element. Okay, so if we plot these two vectors a1 and a2 within uh, within the plot, and we also plot the original data points we simulated. So this is exactly the data set that was shown previously and simulated. Okay, so here this is our first predictor, second predictor. So these are the data point X that were simulated previously. So the scale of the figure is a bit different, so they might look a bit different, but it's really the same data. And we see here that the vectors here, they might be more suitable to serve as axes in that to and summarize that data, because as we said, we could summarize very well the location of each of these points in 2 dimensions by their location across this axis. Okay, so the location of the points across this axis here, or the first vector a1, can very well summarize the location of the point, and the departure of the location on that axis, so the coordinate on this second axis, which is orthogonal to the first one, is very negligible, so we might be able to neglect it and still have a very good representation of each of the data points. So this shows that the canonical basis, which is basically the vectors vertical and horizontal like this, it might not be the best choice to represent our current data. Maybe a set of axes like this might be better. And why that vector? It's because if we go back, I'll go back a few slides. When we simulated the data for the second coordinate, we had roughly that the second coordinate was roughly 3 times the first coordinate. Okay, so because of that, this is why it makes more sense to have a vector in this direction, where this second coordinate is 3 times the first one. Okay, so here we see visually it makes sense. Later on in the chapter, we'll try to explain how to find these original set of basis vectors to optimally represent our problem. But now let's just say we'll stick with these and won't try to describe how we've obtained these. Well, we did like a bit informally, but we won't discuss the optimization of these vectors. We'll just try to see if we take these basis vectors, what happens. Okay, so the idea, if we go back 2 slides, we said that any data point could be represented as this combination. So basically a weighting of the unit vectors, where the weights are the coordinates in the vector of the vectors or of these axes, which are basically the elements of this vector. Conversely, any data point can also be represented as the coordinate across the first new vector a1. So A's, the A's are the vectors in red in the previous slide. So the coordinate across vector or axis a1 plus the coordinate across axis a2 times the second vector a2. So xi has 2 representation, one in terms of its coordinates with the canonical basis, second one in terms of its coordinates with the new basis of vectors. Okay, so because of that, we can have the following representation. So if we do that, the xi can be expressed as this matrix A here, where we stack vectors a1 and a2 times the vector zi, which contains its coordinates in terms of the second set of axes. So this equation allows to calculate these new coordinates based on the vectors here and the original observation. So if we want to find the coordinates, it's pretty simple. We invert the matrix A and multiply by this on both sides. So the set of coordinates with respect to the new basis vectors contained in A are given by Zi. So Zi is the vector of all such coordinates for observation I. It's A inverse times the vector xi, where Z and X, they're column vectors. Okay, so here, if we want to do that simultaneously for all data points, we want to get the new coordinates for all data points, we can stack these equations into a matrix. So here, this leads to z1 until zn, or z1 until zn being so each of these z's are column vector, but we can stack them together to have a matrix, and this would be equal to A inverse times x1 until xn, which are which is the matrix containing all features of predictor data point x1, all predictors of observation x2 until all predictors of observation xn. So this guy here, it's basically like if we want to compare with a regression setting, this is basically equal to the design matrix without the row of ones, of course, but this is the design matrix that is transposed. Okay, so it's good. We can express the data points in terms of their coordinates in the original system of axes, the unit vectors, and all such coordinates are found in this matrix. Or alternatively, we can obtain this new matrix of Z, where here each column of that matrix Z contains the coordinates of the associated ith observation and coordinates in terms of these new axes, or these two new basis vectors. And if we do that, let's try to see what happens to the sample standard deviation of the two coordinates. So here, if we look at this matrix here, for each of the coordinate, we can calculate their sample standard deviation across all observations. Okay, so for example, you take the first coordinate, so the coordinate in the first axis, do its sample standard deviation for across all observations, do the same for the second, and we see that the standard deviation for the first coordinate becomes much larger than it was in the past, so 3.05, whereas the standard deviation, the variance for the second coordinate, so I said standard deviation, but it's really, S square is really the variance. The variance for the second coordinate in the new set of axes is negligible. It's very small. So because of that, we have that the variance of the second coordinate in the new set of axes is very small. And moreover, so here we haven't showed that. We'll show that only in future a few subsequent part of the chapter. But it can be shown that the average across all observations of each of the coordinates must be 0. So because this is the case, the second coordinate, it has an average of 0 and its variance is 0, so it's approximately 0 all the time. Which means that when we have the following equation, so we can say we represent xi as its first coordinate in terms of the new axis times the first basis vector plus its second coordinate in terms of the second axis times the second basis vector. When we do that, because the second coordinate is always almost equal to 0, we can neglect that term and we can have a very good representation of xi simply by writing it as its first coordinate with respect to the first new axis times the first basis vector. So we can see that the original data, which was two-dimensional, could be extremely summarized extremely well by a one-dimensional data, which is its coordinate with respect to the first diagonal axis, because its coordinate with respect to the second one is negligible. And this is what we saw earlier. So we see that the coordinate across this axis is very large, but the coordinate across this axis, it's negligible, so we can almost remove it and do a very good approximation of all data points. Okay, one interesting thing we notice is the following, is if we sum the variance of coordinates for the z's, so the coordinates in terms of the new set of axes, we obtain 3.061, which is exactly identical to the sum of variances for coordinates in the first set of axes, which was the canonical basis. And why is that the case? This is simply due to the Pythagoras theorem. Okay, so I'll draw a quick picture here to illustrate that. So let's pick, I don't know, this color. So here, let's say this is here, and let's say we have a point here. So the original set of axes is the canonical one like this, and let's say our new set of axes is basically something like this and something like this. So the idea here, if you sum the square coordinates for this point, under any of the two set of axes, you should have the same result. Okay, because if we do that, let's consider a new color. So you might consider this point as being, okay, so this coordinate squared plus this coordinate squared. So this is the length of this is the coordinate with respect to the second vector. This is the coordinate with respect to the second vector. And here, so this is one way to do that. And the other way to represent this point is across these axes. Okay, but the idea here is if you sum the the length of this green line square and the length of this green line square, it should be exactly equal to the square of this coordinate plus the square of this coordinate. Why is that the case? It's because the sum of this square plus this square is the distance. I'll have a new color here. So through Pythagoras theorem, this segment square plus this segment square is equal to the length of the pink segment square. Conversely, this segment square in green plus the length of this other segment square in green, once again through Pythagoras theorem, it's the length of this pink segment in square. So both, if you sum this square plus this square, it should be equal to this square plus this square. Okay, so the sum of squared coordinates in the first set of, or the second set of axes should be equal to the sum of the squared coordinates under the second set of axes. Okay, and for this reason, we will have that if we do that, we could sum across all observations I and divide by 1 over n. So if we do that, and we can do that on both sides, 1 over m, you sum across I, and from that, this directly gives this, because recall, the s square, it's the sum of zi minus z bar. Okay, so but z bar, we said that it's always equal to 0. We will show that subsequently. And x bar is also equal to 0 because x bar is a centered data. So this is basically the sum of the zi. So s z j is zij minus here, which is the sum of zij squared. So we can see that when we sum, here and here. On the left side, we have that the sum of variances of all coordinates for the new set of axes, and on the right side we have the sum of variances of coordinates within the second set of axes. So basically what this says is, regardless of what set of coordinates we will use, if we use an orthonormal basis, then the sum of variance of coordinates will be remaining exactly the same, so will be invariant to the choice of coordinates. So the idea here is, if we want to minimize the variance for one of the coordinates, which is what we want to do, because if we minimize the variance for one of the coordinates, we might be able ultimately to drop off this coordinate and to do an approximation because it's negligible. Then this entails that you would obtain the coordinate variance, which would be very large for the first one. Okay, so the sum of variances across all coordinates is invariant. So if you want to reduce the variance for one coordinate, you need to shift that variance to the other coordinate. And for that reason, to find the most suitable set of axes, what we'd like to do is we'd like to find vectors for which that variance is initially very large, because if the variance of the coordinate of that vector is very large, then this one will be very low, and we will be able to neglect this coordinate and have within our data set, and therefore obtain dimension reduction by having less variables. So this is roughly the idea we use in principal component analysis. Okay, here this showing this leads to this. This is what we're gonna do next. So I've basically shown it, but let's go through these steps a bit more slowly. Okay, so we just showed that the sum of squared coordinates for the new set of axes is the sum of squared coordinates for the old set of axes. And again, so to go from here to here, recall that when you do Zij or Zij minus its sample average, it's the same thing, because for x, it's clear why we can subtract the average, because the average for each predictor was 0. And why is it 0? It's because we said at the onset that we consider only centered predictors, because PCA is only applied on centered predictors. Now for the z, it will be shown shortly that having centered predictors for x will lead to also centered coordinates for the new set of axes. So the average of coordinate for all new predictors j should be equal to 0 also. Okay, so when we have that, as we said, we can divide by n and sum with respect to all the i's on both sides, and this entails that the sum of the variance for the new coordinates across all predictors is the sum across all predictors of the variance of coordinates for the original predictors. So the total variance, and by total variance it's the sum of variance of coordinates across each individual predictor, is invariant to the change of basis we do. Okay, so as we said, I've said it also like two slides ago, but let's repeat that a bit more slowly just to make sure we understand. Okay, so in the previous example, we had originally two coordinates to represent a data point, but we showed that this data point could be very well approximated by knowing a single random or a single variable z1. So we had that this data point could be very well represented by z1 times the vector a1, which was the first basis vector. And because z2 was negligible, if we want to remove z2 from our new data set, it would be fine because it provides limited information and is of because it's of limited magnitude. Okay, so the loss of information provided by omitting Z2 is very low, and therefore, instead of working with a two-dimensional data set, we are able now to work with a data set with a single predictor, and which summarizes very well the information provided by the original one. Okay, so and because of this, we've achieved dimensionality reduction, and we can work with data which has smaller reduction. So here in this simple example, we go to from two dimensions to one dimension. So it might seem okay, it's not that much, but when we have very large data sets, so if you start with 1,000 predictors and you can come up with 7 predictors instead, you might be very happy in that case to summarize, to have this kind of dimensionality reduction. So we can see that for large data sets that can be very useful. So we'll stop the lecture there, but for within the next lecture, we will tackle the more general case where first we generalize into higher dimensions. So instead of having p is equal to 2, we'll consider a general p. And the second thing we will consider next is the identification of this optimal set of axes, or this optimal orthonormal basis. How do we find this in practice for some given data? How do we optimize the basis vectors to get the best possible representation of the data and get the best, the smallest loss of information when we reduce the dimensionality of our data? This is what's going to be discussed in the next lecture.